You know, our world runs on conversations that we never, ever hear. They're these silent, invisible dialogues happening at the speed of light between all of our machines. I mean, from checking the weather on your phone to streaming a movie, it is all powered by a secret language. Today, we're going to pull back that curtain and decode that language. We're going on a journey from a simple on or off switch all the way to the complex, structured conversations that make our digital lives possible. So let's just dive right in and start decoding.
Seriously, think about it for a second. You tap an icon on your phone and boom, in an instant you get the exact temperature, the humidity, the forecast right where you are. Your phone app, which was built by one company, somehow has to ask for information from this massive government weather server built by a completely different team, maybe even decades earlier. So how do they know how to talk to each other? What language are they even speaking? Well, I promise you, this isn't magic. It's a beautifully designed system, and we're about to break down exactly how it works, starting at the very, very beginning.
Before we can understand a conversation, we first have to understand its alphabet. And for all digital machines, that alphabet is unbelievably simple. It's not made of letters or sounds. Nope, it's made of states. It's the language of light and shadow, of on and off. And this right here is the absolute foundation of everything that follows. So the smallest possible piece of information in the entire digital world is called a bit. And a bit can only be one of two things: a 1 representing on or a 0 representing off. The source material gives us this fantastic analogy. Imagine you're with a friend in a dark field and all you have is a flashlight. A quick flash of light, that's a 1. No flash, that's a 0. That's it. That is the entire language at its most basic level. And this isn't just a cute analogy. It perfectly mirrors the physical reality inside every computer, where billions of tiny electronic switches are at any given moment either on or off. Okay, so a single flash of light is pretty limited, right? But what happens when you start stringing them together? This is where the real power comes from. By lining up bits one after another, we can create more and more complex messages. And the number of unique messages you can create follows this simple, powerful formula you see here. 2 to the power of n, where n is just the number of bits you're using. So with 2 bits, you get 2 squared, or 4 unique signals. With 3 bits, you get 8. With 8 bits, you get 256. It scales up exponentially, and this is how we build incredible complexity from the absolute peak of simplicity. So let's take those 3 bits. Our formula tells us we can create 2 to the power of 3, which is 8 unique combinations, 8 distinct signals. Now that could represent anything we agree on, maybe the numbers 0 through 7, or 8 musical notes. Or, to make it a little more fun and tangible, let's talk about pizza.
And this just illustrates the whole concept perfectly. Let's say we assign each of our 3 bits to a different topping. The first bit is for pepperoni, the second for mushrooms, and the third for onions. If we send the signal 000, that means no to all 3, a plain pizza. A signal of 100 means yes to pepperoni but no to the others. What about 101? Well, as you can see, that would be pepperoni and onions. As long as we agree on this simple code beforehand, we can communicate one of 8 specific pizza orders with just 3 simple on or off signals. This is exactly how machines build up meaning.
All right, so we know how to use bits to represent a few choices, like pizza toppings. But how in the world do we get from there to representing the entire spectrum of human language? All our letters, our numbers, our symbols. To do that, we need more than just a simple code. We need a universal dictionary, a shared standard that every single computer in the world can agree on. We need a codebook. And that dictionary is called ASCII. That's the American Standard Code for Information Interchange. You can really think of ASCII as the Rosetta Stone for computers. It's basically a big list that assigns a unique number, from 0 to 127, to every uppercase and lowercase English letter, every digit from 0 to 9, and all the common punctuation marks. It created a standard way for every machine to interpret sequences of bits in the exact same way. It's the reason a 1 followed by 6 zeros and another 1 will always be understood as the letter A.
So let's see how this works in the real world. Take a look at this table. In the ASCII dictionary, the uppercase letter A is assigned the number 65. The letter I gets the number 73. Machines then take these numbers and convert them into binary. Now, a standard block for a single character is a group of 8 bits, which we call a byte. So, as you can see, the number 65 becomes the byte 01000001, and 73 becomes 01001001. So to a machine, the word AI is literally nothing more than this sequence of 16 ones and zeros. It's just a chain of bytes, each one a precise, universally understood symbol.
Okay, we're now at a really crucial point. We've established that machines have this universal codebook, but their true power,
Their secret weapon, really, lies in something that human language can never have, a complete and total lack of ambiguity. Human communication is messy, right? It's full of context and nuance that can lead to misunderstandings, while machine communication, by its very design, eliminates that problem entirely.
This slide right here, this is the aha moment. It illustrates a concept called the semantic triangle. For us humans, there are three parts to meaning. There's the symbol, the word we use, like apple, the referent, the actual thing, and the thought, the idea or context in our mind. The word apple could mean a fruit, a tech company, or even a person's name. It's that thought layer that creates all the potential for confusion. But look at the machine side. The symbol, that binary code 0100001, has a direct, absolute, one-to-one link to its referent, the character A. There is no thought. There is no context.
And that is the secret. That is why all of this works so perfectly. No thought, no context, no confusion. This absolute precision is the bedrock upon which all reliable digital communication is built. It guarantees that when one machine sends a message, the receiving machine understands it exactly as intended every single time.
Okay, so we get how a single machine can process text with perfect precision. But what about our original question? How does your weather app talk to a totally separate weather server? I mean, these are different programs built by different people, maybe in totally different programming languages. They need a messenger, an intermediary to manage their conversation for them.
And that intermediary is the API, which stands for Application Programming Interface. An API is basically a set of rules and tools that lets one piece of software make requests and get information from another piece of software in a standardized, predictable way. You can think of it like a contract that two programs agree to follow so they can communicate without needing to know anything at all about how the other one works on the inside. Honestly, the best way to understand an API is with the waiter analogy you see right here. You, with your app, are the customer in a restaurant. The server, with all the data you want, that's the kitchen. Now, you don't just walk into the kitchen and grab your own food. That would be total chaos. Instead, you give your specific order to the waiter. That's the API. The waiter takes your structured request to the kitchen. The kitchen prepares exactly what you asked for, and finally, the waiter brings the finished dish, the data, right back to your table. The API manages that entire conversation, from the request all the way to the response.
Now, for this whole digital waiter system to work, the order has to be perfect. It can't be vague. You can't just tell the waiter, "I want food." You have to specify exactly what you want, how you want it cooked, any extras. The exact same thing is true for machine conversation. The request needs to have a precise grammar and structure.
An API request is structured like a precise command, kind of like a mechanical train. We can break it down into a few key parts. First, you have the endpoint, api.server.com. That's the restaurant's address. It tells the request where to go. Next up is the resource, /data/temperature. This tells the server exactly which section of the menu you're ordering from. And finally, you have the parameters, everything after that question mark. Question mark, date equals today. This is your specific detail, filtering the request to get the temperature for today and only today.
So, what does the data that gets sent back and forth actually look like? Well, it needs to be in a structured format that both machines can easily read, and the most common format today is JSON, which stands for JavaScript Object Notation. It's so popular because it's both easy for us humans to read and super simple for machines to parse. Think of JSON as the digital version of a clean, well-organized menu and a perfectly plated meal. It structures all the data in a predictable way.
There's just one last piece to this puzzle. You often can't just send a request to any API you want. A lot of these services are protected, and you have to prove you have permission to access them. This is done with an API key. An API key is a unique string of characters that acts like a VIP access card or a password. As you can see, it does three critical things: authentication to prove who you are, security to keep unauthorized people out, and tracking so the service provider can monitor how much you're using their service, maybe for billing or to prevent abuse.
So let's just quickly recap our entire journey. We started with the simplest possible signal, the bit, the on or off alphabet of machines. We saw how those bits are grouped into bytes and translated into human characters using a universal dictionary, ASCII, which removes all ambiguity. Then we brought in the API, our digital waiter, who manages conversations between different programs using that structured request-response cycle. And finally, we saw that the data in those conversations is all neatly formatted using JSON.
If there is one single thing to take away from all of this, it's this idea right here.
Precision is the bedrock of technology. From the unambiguous nature of a single bit all the way to the structured grammar of an API call, this entire system is built to eliminate confusion and make sure that messages are sent and received with perfect fidelity. This relentless pursuit of precision is what allows our complex, interconnected digital world to actually function so reliably.
We've done it. We've decoded this secret dialogue. You now understand the fundamental principles that allow your phone to talk to a server on the other side of the world. You know the language, from its basic alphabet all the way to its conversational grammar. So the only question left is the one you see on your screen. Now that you know the language of the machines, what conversation will you start next?